We're very close to the end of the semester, and I hope everybody's doing well. There's one last principle that we need to talk about, and that's what today's lecture is going to be about. And specifically, it's about proportion and scale. Now, there is a good possibility that I will have a lecture, maybe even on Thursday, that probably will deal with file types. For example, JPEG versus a GIF versus a PDF versus a PNG versus a TIFF. And there's also one that I probably will do on additive color. I'm hoping I can get those in. But today's lecture is on proportion and scale. All right, proportion. Well, proportion deals with the relation of individual parts to one another within a composition. For example, if we were to take one thing and relate it to another as part of the whole. Proportional parts are considered in relation to the whole, and when related, the parts create harmony and balance. The term scale is used when proportion is related to size and refers to some gauge for relating to parts to the whole. Now, scale is pretty easy to figure out, and I've got towards the end, the last like 3 or 4 slides deal just with scale. For the first part, we're going to talk about proportion, because proportion it's not really a difficult concept, but because of the ancient Greeks, it became kind of mathematical, and most art people aren't technically mathematically inclined when it comes to certain things. We tend to be more kind of a free spirit. An example is that the human figure is often considered the norm by architects for scaling buildings, as well as by artists for representation in their artwork. Well, when we talk about proportion, probably what should come to mind is that we deal with mathematical things that were developed a long time ago. One of those is the golden mean. The golden mean, sometimes called the golden section, to represent the ideal standard for proportion and balance in art. And mean just means the average, the golden average. The golden section, as it applies to works of art, stated that a small part relates to a larger part as a larger part relates to the whole. Now, I've got an example here of Michelangelo with the Spark of Life or Birth of Jesus, depending on where you read about it. And we can kind of see that there's a relationship here. If we look at this right here, this is considered the golden average. We have, or a rectangle, golden rectangle, both are considered roughly the same. There's a little bit difference, but we'll get to it. We look here, and Adam is 1/3 the size of God. And because we're humans, we kind of feel comfortable with this. This makes sense to us. And we can see that Michelangelo used it to make his work more interesting. So the golden section, a small part relates to a larger part as the larger part relates to the whole. So as we were looking at this, we compare this, and then to the whole thing. Now, to create the golden rectangle, I actually have a video that I'm going to play in editing that I've already done, and it's fairly simple. To be honest, I didn't get it the first time I was told about it in undergrad. I mean, I kind of got it. I understood the philosophy of it, but I didn't really understand how to create it. It's basically fairly simple. This is the golden ratio. We have A to B, and then C is placed right here. Now, if we were going back to Michelangelo's work that I just looked at, we could see that this was probably the same distance as Adam was, and this was God. All right, so this is the ultimate golden mean. Now, we can create the golden mean several different ways, but probably the easiest and the way that I like to do it, if I ever do it, I mean, technically you get to a point where it's kind of built into you. You all kind of figure it out over time by doing critiques and by just kind of working with art. Eventually you'll come to the same conclusions as the Greeks did, but they did it mathematically. And that's what I want to show today. So if you're aware of how mathematically it's created, it maybe makes sense why you're looking at art, why something looks better than something else. Right, so this is the goal right here. The first thing we need to do is to create a square. Once we create a square, we need to change that into a rectangle. But our problem is we don't really know how far to go out for this square to have the correct proportion to turn it into a rectangle. We could kind of guess. Our eyes would probably tell us it's roughly about here. But mathematically, what we would do is we would find the center point here, which is right here, right? And we would take a compass and do an arc down to this point. Once we have this point right here, we draw from here to here, and from here to here, and here to here. And like I said, I have a video, and I'm going to play it in just a minute. But this gives you where I actually do the steps down in my office. This is what we're trying to do. Now, once you get to this point, we have the perfect rectangle. And by perfect, it doesn't mean that numerically it's perfect. It means it's perfect as in the Greeks thought that the proportions, that by doing it mathematically, we get to a perfect proportional rectangle. Now we could take that rectangle and put it up against other pieces of art and say, well, if this is perfect and the artist did this in their work, then their work is proportionately perfect. The one thing that we don't really know about here is that third. And in order to figure out the third, it's fairly simple. We just go up into this upper left point and down to the lower right point, and we draw a line to it, just like they've done here. And where that line intersects with the C, we draw a line horizontally across. And now we have a third here and 2/3 up here. And this is considered to be proportionately correct in art. Okay, I want to show you how to do the golden rectangle. It's pretty simple, and it's a little bit tougher to do it on the computer, so I figured I'd do it by hand to kind of give you an idea of how to create it. Now, the golden rectangle kind of applies to the way proportion, what we consider to be proportionately attractive. All right, I'm also going to show you the rule of thirds. So I've got a perfect square here. It's a ratio from 1 to 1. Okay. The height is the same as the width. And the first thing that we need to do in order to figure out the second part, because a perfect square, to add that extra area, we need to know how far out to go to make this rectangle proportionately correct. So there are simple ways to do that. The first is we need to figure out the center between both of the vertical lines. So figure out the center somewhere in there. I'm going to measure this, 16 to 24, that means it's 8. So I will go 4. Looks like it's 22. Now, I'm not trying to be exact on this. I'm trying to just show you how you would do it. So bear with me if I make, the lines aren't exactly straight. Okay, now that we have this, this gives us the information to figure this out. And we do this by using a compass and putting it on that center point. And we need to figure out that corner, which is roughly about there. And then all we have to do is just drag this down. Now, the two things that we're concerned about is this horizontal line at the top and the horizontal line down at the bottom.
So I'm going to take this up, and hopefully I can get this right. And I'm going to draw this line. I'm off a little bit. What I did is right where at this point to this point. The next thing I'm going to do is I have to figure out the top as well. So I'm going to do exactly the same thing. I'm going to come back. Now I'm trying my best to have perfect lines, but my guess is it's not going to be perfect. I'm going to come over here and continue this line over, and then I'm going to connect this point to whatever point this is up here. And I'll do that by put this here, put this here. Let's see, kind of get that down. And hopefully, all right. Now, like I said, it's not perfect, and I hope you understand it. I'm just showing you how you would create this. Now, to find that proportion, or the 1/3, what I'm going to do is I'm going to take from point to point, from this corner here to this corner here. Now, I didn't fill that in very good, so I'm hoping I'll get this right. I'm going to go here to here, and a line straight across, and this gives us our 1/3 mark. So now I just need to come across here and draw a line, kind of bring it up a little bit from there to there. Now, like I said, I didn't spend a lot of time trying to get this perfect. If I would have done it properly, I wouldn't have a camera over my shoulder, and I would be using a T-square, which I don't have with me this morning while I'm doing this recording. So my lines aren't necessarily perfect, but you get the idea.
Now we owe this to the Greeks. The ancient Greeks devised special proportional standards for their figurative works. These standards are found in their sculpture, and they are considered to be the Greeks. Now, it could be argued whether the Greeks were the first to come up with their sculpture represented the perfect human form. You can see what they were trying to do with their sculpture. The scale that they used was based on mathematical rules that established ideal relations of human parts. Now remember, we're talking proportion. You know, how far should this be from the kneecap be to the heel? The Greeks figured this out. Now, in most of your classes, when you do drawing, you look at something and you draw it, and you just you draw as far down as you think it's supposed to go, and you will eventually get that same proportion. But the Greeks put it into mathematics. For example, the figure was determined to be 7 1/2 heads tall. So if we were to take the head of the spear bearer here and dislodge it or measure it and go down 7 1/2 heads, that's the perfect height for this person's head. The distance from the top of the head to the chest was said to be 1/4 of the total height. So now that we have the height, we divide that by 4, and we can get from the head down to the chest by that measurement. The distance across outstretched arms is equal to the height of the body. Well, you think about it, and we kind of know that this is true. Online, there's all sorts of different ways that you can measure it. They say take a piece of yarn and tape it to your fingers and put it out, and you can figure out how tall you actually are that way. The culture of the spear bearer, this is this image right here, is sometimes considered the canon because it best demonstrates the standard for figure proportions, for human proportions. Now this is a replica, the original, this is a Roman replica of the original Greek statue. Now when we look at this, the golden rectangle, we can kind of see how it kind of plays in some part when we look at the American flag. If we look at this, this is kind of 1/3 of the whole, right? If we were to take that golden rectangle and put it up like this, we could see that proportionately it works. It's not over the top, it's one of the reasons why the American flag has endured for as long as it has, is because this blue field right here is roughly 1/3 of the rest of the flag. And over here, this is kind of unique, and as I was looking for images to show you guys, I came across this one. It has all the different proportional relationships of different things. Like, for example, the pelvis is 1 head high. So if you measure the head and you wanted to do the pelvis, it should be the same height as the head. You can see that artists have the proportional relationships kind of figured out by now. So if you're interested on, say, the length of the femur, this right here, then, and how it relates to the rest of the body, you can kind of draw a human without actually just looking and sketching. Not necessarily going to be a good drawing, but you could do it. Okay, the Fibonacci Spiral. Now, because the Greeks, they tried to attribute math to everything around them, they looked at the world and said, well, okay, if mathematics relates to everything, then we need to somehow figure out how we could do the mathematics of a spiral. And there are certain key things that they came up with. Fibonacci is the name of the person who created it, and it's named after him. But he developed this mathematical process of creating it. And I'm not going to actually show you how to do it. It's complicated, and it actually needs like a classroom setting where I sit, now do this, now do this, now do this. But it's not that difficult, but it's kind of hard to get over that initial hump of understanding. So I'll read this though. The spiral curve is created by the projection of the golden mean. If you look, we can kind of see it right here. The inside corner of the square locates the compass point, which scribes an arc from the corner to corner. This line is continued until the next square with a new compass point located in the inside center corner of the square. The process continues from square to square until the spiral is completed. All right. It can be kind of complicated, and I'm not expecting you to understand it completely, but if you have just a basic understanding, I think you might be able to see some of the significance and the simplicity in the way it was created. The first thing to understand is if we imagine, say, a number scale, say 0 through 100. When we look at that, we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we could go on forever. That's kind of the way you would start the Fibonacci spiral. Now remember, the spiral is created by the squares in the previous slide. So the first thing we would do is we start with 0. Remember, our number sequence goes from 0 to whatever. We start with 0 and add the next number to it, which would be 1. So we add 0 plus 1 is equal to 1. Make sense? Now we take 1, the result of the 0 plus 1, and we add 1 to it because it's the next number. See, we started with 0, now we're going to 1. So 0 plus 1 is equal to 1. Now we go 1 plus 1 is equal to 2. Now our sum of that is 2. So we have 2 Fibonacci numbers here, 1 and 2. Now the number 1 is the only single time that we duplicate a number. From now on, we move forward one number at a time. So after we take the Fibonacci numbers 1 and 2, then the next thing we do is we add 1 to the previous sum. So we add 1 plus 2 is equal to 3. We take the number 2 and we add it to the sum. So now we add 2 to the previous sum, which was 3, and that gives us 5. Now we take 3 and add it to the sum, and we get, which was 5, and now we get 8. And we can keep going on and on and on. We take 5 and add it to 8, and we get 13. We take 8, add it to 13, and we get 21. And if we wanted to keep going, we could take 13, add it to 21, and it would be 34. And we could take the next number would be 21 plus 34 would equal, anyway, it goes on and on and on and on and on and on. So anyway, from these equations, the first, what is this, 2, 4, 6, 7 examples, we come up with 1, 1, 2, 3, 5, 8, 13, and 21. And like I said, they could go on indefinitely. So 1, 1, 2, 3, 5, 8, 13, 21. All right, so now that we have the Fibonacci spiral numbers, to create the spiral itself, we have to start off with squares. Now, in the examples that I showed before, they were kind of small, but you should have seen squares in the first two. And those were those first two ones. Remember in this sequence, 1, 1? So we have 1 and 1. Now, the only way I could actually get this to look correct was by multiply it times 100. So all these numbers are multiplied times 100, but you technically wouldn't have to do that if you were working on a different scale. So we have a 1 by 1 square here, a 1 by 1 square here, a 200 by 200, because we have 2 here. We have 200 by 200. Our next number is 3, so I went 300 by 300. Next number is 5. I went 500 by 500. Next number is 8, right here, and I went 800 by 800. Now at this point, I don't have enough room to actually show all of the 800 by 800, and I couldn't really go any too much further. All right, so now imagine that the spirals aren't actually there. We just have these boxes there. All right, so it makes kind of sense the way they're placed. It's 1, 1, 2, 3, 5, 8. So we're kind of, the way it was constructed gives us that spiral. Now the next thing we need to do is find the inside corner of each box, and with a compass or Illustrator, whatever you want to use, you build an arc. And each of these has an inside corner. Now I went to actually label them, and it was getting way too complicated. But for example, this first box, the inside corner, if I look at all four corners, the inside one is this one right here. So, I mean, technically, let me click on it here. No, it's not going to let me. I would go here, and I would do a quarter circle from there to there. Now this one, seriously, this one, no pun intended, this square, the inside corner is right here. So I would do the arc from here to here. Now we move over to the 2 square. The inside arc is right here, or the inside corner is right here, and the arc goes from here to here. Now the next one, the 300 or 3, Fibonacci number 3, the inside corner is here, so the arc goes from there to there. And for 5, the inside corner is right here, and the arc goes from here to here. And the 8 there's really no inside corner when you look at it, but in theory, the next square, which would be 13, here and here, this would be the inside corner right here, and then the arc would go this direction. Okay? It's pretty simple once you do it once or twice. Here we have an example of how the Fibonacci spiral we see it in nature. For example, we have a galaxy here, and we have two spirals that are kind of going in opposite directions. One's coming around this way, and this one's coming around that way. And together they create this very cool shape of the galaxy. Up at the top, we have a nautilus. I don't know if it's a nautilus shell, but it's definitely in that Fibonacci spiral. Now remember, it's mathematics. This describes how this was created. And down here, we have a hurricane coming towards the east coast of the US, and it follows that same path. In fact, the people that put the lines over it show exactly how it works. It's remarkable that the Greeks figured this out. I would assume that further along somebody else would do this as well, but thousands of years ago they had done this. Okay, when we talk about scale is the relation of comparing one item to another. The human body is a good reference when we're working with scale, since we know what the average size of a human is. When we say he or she is tall, we are making a comparison based on the size that we know of the average human. We also use the same type of scale when we talk about proportions in architecture. Here I have an example of mural that shows the scale of the child dwarfing this full-grown man. We know normally when we talked about scale in dominance, we would say if this wasn't here, right? If this man wasn't here, we would say this is dominant because of the size of it, because of the scale of it, not because he's dwarfing this right here. When we talk about scale in proportion, we're talking about how small he is in relationship to how large the child is. So we know the size of an average human being, right? We may not know exactly, but we know that an average human being is roughly, 5'9" or something, 5'10". And if he's 5'10", how big is this painting of the child? Well, we could actually do it. We could do, we'll just say 6 feet. If we were to keep going, we would say 12, 18, probably pretty close to 24 feet. Some other examples of scale. You've probably all seen this in textbooks, or if you haven't, how do we know that this is large? Do we know it's large? I mean, when I look at it, I know it's large, basically because what I do is I scan the whole composition, forget that it's anything other than a composition, and I notice the trees and the small leaves. So in my mind, I'm saying, okay, well, if the leaves are that small, it's either really far away or it's very small. Here we have grass. Now I know what grass looks like. So the relation of the grass to the tree tells me that the grass and the trees are right. This isn't very small. It's not too far away. It's the normal size of what I would expect a tree to be. So now I look at this and I compare what I know to be normal to the scale of this clothespin, and I know that it's very large. So I analyze everything here, compare one element to the rest of the composition, and I determine that the clothespin is very large in scale. Here's an example of what we were talking about, the human form as being a scale of the size of something. Now, if we just saw that T-Rex, or whatever it is, an Allosaurus, or whatever it is, it was just standing there in this image, we don't know if it's, 3 inches tall, 24 inches tall, or it's 12 feet tall. We don't know. But when we see the human figure there, by scale, we know that that dinosaur is very large. And down here is the same basic concept. We have a human for scale. Have you ever seen, I don't know if it's popular all over the web or it's just one of the sites I go to, where they'll put a banana next to something and they'll say banana for scale? Well, it's the same basic concept. When we know that this is an adult female, she looks proportionately correct. Her arms and her head and everything looks like it fits the rest of her body. So we would guess maybe she's 5'6", 5'8", something like that. And if she's that tall, then this is huge. Look at the size of the knots in comparison to her. They're as big as her shoulder. So they're huge. So we know that this is very large compared to the form of the human. All right, so when we talk about proportionate scale, there's 2 ways to look at it. One is based on an artistic interpretation of what we're looking at. And as humans, we kind of develop innate traits to do that. We know that something's large based on what's around it. We don't have to study that. We don't have to find ways to figure out if something is large because it comes natural to us, and that's what scale is. When it comes to proportion, we know when something looks correct or we know when something doesn't look correct. And a lot of times that has to do with the proportion of the object itself. Specifically, I'm talking more about the human figure. You see people with, say, big ears or big eyes. You know that it doesn't look correct because of the proportion isn't correct in, maybe the best way to put this is a smaller thing. For example, 2 eyes. Compare the 2 eyes to the face. If those eyes are too big, we know it's out of proportion because it doesn't fit with what the proportion should be. When you're drawing, if you make the eyes too large, it doesn't work. The Greeks figured out a way to kind of put mathematics into it. Now, it's a little bit dry, but it is basically, to use a word that was used earlier, it is canon, meaning that it is kind of rules that we follow. Now, we don't necessarily have to follow them. They're kind of more like guidelines, but they are there to help us understand what something should be, the size it should be, and how it should relate to the parts around it. And that's key, is the whole composition needs to be in proportion to the individual elements in it. So like, for example, if we were to take one item and compare it to another, and if it's out of proportion to the composition, then we know that it's not correct, that the composition isn't correct as well. Now we can play with that. The clothespin, the example I showed of the clothespin is a perfect example of an artist playing with our sense of scale and proportion, and it makes it much more interesting because our expectation is a clothespin is fairly small. But here we have a clothespin that's pinching the earth. And it takes us maybe a second to realize, maybe not even a second, maybe a half a second to realize that this clothespin is huge and that that's not correct. A clothespin should not be that large, and a clothespin should not have the strength to pinch the earth. And the earth should not like be able to be pinched like that. And so it makes it kind of interesting. But if I was to draw, say, the same clothespin next to, say, a person that was half the size, would it look right or would it look out of proportion? Would it look like I drew the person too small or I drew the clothespin too big? It's hard to say. it could, in the overall composition, if the rest of the composition comes together to support whether something's too large or too small, then maybe you have a decent composition and there's no problems. But if you don't support it with the rest of the composition, you have one element that's out of scale, not proportionate to what's around it, then your whole composition is going to fail. I hope that makes sense. Okay, well, I'm going to let you guys go. I will see you on Tuesday. Thank you.